this video you need to remember the definition of a quadratic form, and now we're going to discuss the definiteness of a 2x2 quadratic form, just to start us off, and we'll talk about definiteness in general once we have a good idea for the 2x2 case. But the 2x2 case is pretty simple to understand. So let's get some examples out there. So Q1, our first quadratic form of, so this is a 2x2 quadratic form because it's related to a 2x2 matrix, and this will be x1 squared plus x2 squared, which is equal to x1, x2. Our 2x2 matrix in this case is going to be the identity, x1, x2. We'll notice that this is always greater than 0 if x1, x2 does not equal 0. So we say that Q1 is a positive definite quadratic form. And sometimes we'll abbreviate this and we'll just say it's pos def because it's two relatively long words. Now Q2, x1, x2 is equal to negative x1 squared minus x2 squared. This is given by x1, x2 matrix multiplied with negative 1, 0, 0, negative 1, x1, x2. Well, you can note that this is always less than 0 if x1, x2 does not equal 0. So Q2 is negative, or neg definite, neg def. Now what does this guy look like, right? So for the positive definite, the unique global minimum of this quadratic form is at 0, and it's exactly 0. And so if we draw this, it looks like a parabolic bowl. For the negative definite case, at 0 we have a unique global maximum, which is 0, and the bowl is inverted now. So this is a situation where I have a minima, and here I have a maxima. That's great. So in some sense, this is what positive definiteness and negative definiteness guarantee us. Now suppose that we have Q3 of x1, x2 is equal to negative x1 squared plus x2 squared. Well, this guy, since I can plug in a non-zero x1 here and the same value for x2 here, I'll get 0. We'll call this guy indefinite. And what this guy looks like is, well, I've got in the x direction I've got negative values, or I've got a downward concave shape, and so what it looks like around 0 is a kind of a saddle picture. So that would be 0, and here's that thing. That's the picture that you would have, and there's ambiguity about exactly whether this is a minimum or a maximum. but it is a critical point, right? You can check that the gradient of this guy vanishes at that point. So we would call it a critical point. Well, how about Q4, x1, x2 is equal to x1 plus x2 squared. Well, this guy is always greater than or equal to 0, but if x1 is equal to negative x2, it can be 0. So we're going to call this guy positive semi-definite. Positive semi-definite. That's what we'll call this guy. Q5, x1, x2. Let's say the negative of this guy. That's the simple one. x1, say, minus x2. It doesn't really matter. Squared. Well, this guy is going to be negative definite. Or negative semi-definite, rather, sorry. So what do these things look like? Well, they look like parabolas that kind of extend forever in a particular direction. So if I'm positive semi-definite, then I have kind of a downward sloping thing. Or I have a downward concave sheet. But it basically looks like a trough. That's the shape of it. And here's the line x1 is equal to negative x2. And if I have a negative definite, negative semi-definite, so this is positive semi-definite. That's the graph of it. And a negative semi-definite is kind of the same thing, only now I'm like a tent. So this is negative semi-definite. So this guy, there is a global minimum for a positive semi-definite, but it's not unique. Here there's a global maximum, but it's not unique. That's kind of the important idea, right? And we're always interested when we have a unique optimum or a unique or a non-unique optimum to any particular problem. And so it's good to study these things, right? So let's figure out when we have positive definiteness for a particular quadratic form. So let's look at the 2x2 case. Let's suppose q x1 x2 is equal to x1 x2 times a matrix a11 a12 a12 a22. So I just assume that this thing is symmetric. x1 x2. Well, this is positive definite if and only if a11 is greater than 0 and the determinant of a11, a12, a12, a22 is greater than 0. And the proof is not so bad, so let's just go through it. But it basically comes down to, well, in order to check for positive definiteness, which is then equivalent to I have a unique global minimum at 0, right? In order to check for that, I only have to compute a sequence of determinants. For the 2x2 case, I only have to compute 2 of them. And then I know the exact behavior. So let's get the proof. Well, the trick really is to complete the square. So we've got q of x1, x2 is equal to, writing it all out, x1 squared plus 2a12 x1 x2 plus a22 x2 squared. And so we're going to add a form, well, we're going to add and subtract a number to complete the square. So in order to complete the square, we're going to add, let me think here, how about a12 squared over a11 x2 squared minus a12 squared over a11 x2 squared. And what does this get us in the long run? Well, now we can factor, and we're going to obtain a11 times x1, right? So we're going to combine this term, and now we've completed the square with this term. So plus a12 over a11 squared. So if we multiply that out, what do we get? Oh, and we should have an x2 here. x2. So when we multiply this out, what do we get? Well, we'll get x1 squared, a11, and we'll get 2a12 over a11 x2. Multiply that by a11, we get this term, and then the final term is just, of course, this guy. But then we have kind of the mess left over, which is going to be a11 a22 minus a12 squared divided by a11, and that's x2 squared. Alright, so now we've completed the form, right? So that means that, so let's look at it. So if a11 is greater than 0, and the determinant a11, a12, a12, a22, which is equal to a11, a22 minus a12 squared, which is this guy here. If this is greater than 0, then, well, that means that this number, a11, is positive. This is a square, so it's always positive as long as x1 does not equal x2, or this thing doesn't vanish completely, right? If it does vanish completely, then that means that x2 had to be non-zero, or that x1 had to be 0 and x2 would have to be 0. This guy is always positive, and this guy is always positive. So this will only be 0 at 0, otherwise it's positive. Therefore, since this quantity and this quantity are non-zero, and of course that means we can divide by these guys, then we have that Q is positive definite. On the other hand, if there is a non-zero actually, on the other hand, let's try to show the contrapositive, right? So the contrapositive says that if well, let's suppose a11 is less than or equal to 0. Well, then of course there's going to be a number that we can plug into here, so we just set x2 is equal to 0, right? And then x1 can be anything. So this term will vanish, x1 can be anything, and therefore we have q, then say x1, x2 equals 1 comma 0 yields q of 1 comma 0 is less than or equal to 0. And so not positive definite. If A11, A12, A12, A22 is less than or equal to 0, then we then see that Q of 0, 1. Well, this term will now be less than or equal to 0. We've killed off the x term, right? Actually, so the trick is we're going to set x2 to be a non-zero number. So what we really want to plug into here is, say, 1 and A11 over A12. So we're already assuming that this is not 0. So negative, say negative 1. Well, this is, of course, a non-zero number, but when we plug it in, we'll get 0 here. We get a non-zero value over here, but this is negative, or equal to 0, so this guy will have to be less than or equal to 0. So Q is not positive definite. And that completes the proof.